All right, thank you everyone who got up early after the lovely last night's session, which is very, very interesting. All right, so I'm going to talk about Big Ramsey degrees. The beginning is things you've seen already, so nothing new for the next 10 slides. This is all background. There's the finite Ramsey theorem, there's the infinite Ramsey theorem, which is really a finite dimensional Ramsey theorem. And then there's the Galvin-Perkry theorem, which is an infinite dimensional Ramsey theorem. So the finite Ramsey theorem is coloring finite sets inside finite sets, looking for a large enough finite set where you can get down to one color. The infinite Ramsey theorem is coloring copies of a particular finite set inside of the natural numbers and looking for an infinite subset where you can get down to one color. And then the Galvin-Perkry is close to the best that you could get if you want to color infinite subsets of the natural numbers inside the bare space. So now we go to a short background on structural Ramsey theory. So you have the analogs of those three theorems in terms of structures. You may be coloring finite structures within some class of finite structures. You may be coloring copies of a finite structure inside an infinite structure, where then your task is to find a subcopy of your infinite structure where all of your finite structures have one color, or maybe as finitely many colors, some bound. And then infinite dimensional structural Ramsey theory is concerned with coloring copies of an infinite structure inside of a given infinite structure. And for these, we look for analogs of the Galvin-Perkry theorem or Silver or Ellentuck. Okay, so a little bit of notation. I'm going to mostly center on a couple of examples today, but in the broad scheme of things, this is what we have. So we have, for finite structures A and B, we'll write the A embeds into B using this notation. And then the B choose A is denoting the collection of copies of A inside of B. A class K of finite structures is then said to have the Ramsey property if it satisfies the Ramsey theorem, but within the class of finite structures. So for the actual definition, if you're given A less or equal B in your class K and some number of colors R, then you can find a large enough but still finite C in your class, where whenever you color your copies of A and C into R colors, there's a copy of B and C, so that your coloring on the copies of A inside of that copy of B is one color. And there's been a lot of work done in this area since the 1970s, beginning with Neschitrel and Riddle, and with also Abramson and Harrington. And some examples to keep in mind are the collection of finite linear orders has the Ramsey property because that is Ramsey's finite theorem. And then what was new in the 70s is finite ordered graphs as a collection, as a class, have the Ramsey property. Finite ordered k-partite graphs, and so forth and so forth and so forth. Okay, so many, many examples of classes of finite structures with the Ramsey property. Ongoing work. Then if we're going to look at infinite structures, okay, a class K is called a Freisey class if it has the hereditary property. So substructures of the form to be in that class are actually in the class. Has the joint embedding property, which means that if you have two members of the class, they jointly embed into a third member of the class. And most importantly, the amalgamation property, which says that if you have a structure embedding into two different structures, you can complete the diagram so that it commutes in a fourth structure, where the copy of A going this way ends up the same place as the copy of A going that way. Okay, so there's an important distinction between universal structures and homogeneous structures. So a structure is universal for a class K if every member of that class embeds into it. And a structure is homogeneous or ultra-homogeneous if every isomorphism between two finite substructures extends to an automorphism of the whole structure. Now, there are many, many different universals for a given class K. There's even many, many different universals for a given infinite structure. But up to isomorphism, there is only one homogeneous structure. And so the Freisey limit of a Freisey class is up to isomorphism, the homogeneous structure that is universal for that class K. Okay. So examples of Freisey structures are things you've seen most of your life, like the rationals are the Freisey limit of the class of finite linear orders. The radograph is the Freisey limit of the class of finite graphs. The random k-partite graph is the Freisey limit of the finite k-partite graphs, and so forth. And when we wish to do finite dimensional structural Ramsey theory, we run into some obstacles with getting a direct analog of Ramsey's infinite theorem. So to set some terminology, if you have a Freisey class of finite structures with a Freisey limit k, we'll say that that infinite structure has finite Big Ramsey degrees. If for each finite k in your class, your Freisey class, there is some number bound t, so that no matter how you color your copies of A inside of K into R colors, you will find a copy of the infinite structure, so isomorphic subcopy of the infinite structure, where all of the copies of A have no more than T colors. Okay. And the Big Ramsey degree of A and K is the least such bound T if it exists. It doesn't always exist, but sometimes it will exist. And if we say that the Big Ramsey degree of A equals 1, that means we have a direct or exact analog of Ramsey's theorem. And we know for a fact that most of the time this is not going to be the case. And then the question is, can you find bounds? What are those bounds? Can you characterize those bounds, and why do they exist? Okay? And at this stage in our collective investigation of this area, we know that the Big Ramsey degrees are really about the optimal structural expansion of K, so that in that expansion you have a direct analog of Ramsey's infinite theorem. Okay? So you're looking for some structural expansion with finitely many extra relations so that you get a direct analog of Ramsey's theorem. Okay, so going back to 2005, we have this KPT correspondence, which motivated a lot of work in Ramsey theory, structural Ramsey theory, since that time. And they found this connection between the Ramsey property and extreme amenability of the automorphism group of the Freisey limit of a class. And in that paper, they asked a whole bunch of questions, including these, about Big Ramsey degrees and infinite dimensional Ramsey theory. So they asked about which homogeneous structures have Big Ramsey degrees. Might they be infinite for certain structures? They asked about the topological dynamics corresponding to Big Ramsey degrees. And they also asked about infinite dimensional Ramsey theory for homogeneous structures. So Andy Zucker proved one direction of this correspondence for Big Ramsey degrees in terms of something he coined a Big Ramsey structure, which is this optimal expansion of K into another structure where you get the exact Big Ramsey degrees being 1 in that expanded structure. Okay, going to infinite dimensional Ramsey theory, back on omega, we'll say that a set is Ramsey if for each m in our bare space, there is an n in the m cube, where the n cube is either contained in X or disjoint from X. And the axiom of choice, or even just the existence of a non-principled ultrafilter, can give you a coloring where you can never get down to one color here. So an idea that's attributed to Dana Scott in the Galvin-Perkery paper is that if you should try to restrict yourself to some definable sets, okay? So, oops. All right. So Galvin and Perkery proved that Borel sets in the Baire space are Ramsey. Ramsey is the terminology in Todorcevic's book. Completely Ramsey is the terminology that was in Galvin-Perkery paper. And then Ellentuck very quickly afterwards used what they did in this paper to make a topology, which then completely characterizes the Ramsey sets as those that have the property of Baire in the refined topology. And then this gives rise to the notion of topological Ramsey spaces, of which I'm very fond, which is taking this idea and then expanding it to many other different types of topological spaces. But they all have these things in common, which are that points are infinite sequences, and the topology is induced by finite heads and tails, infinite tails. So the natural refinement of the metric topology on these spaces. And then they have the key property that every subset with the property of Baire is completely Ramsey. So these were developed mostly for spaces of infinite sequences of words by Carlson and Simpson. And then Todorcevic, in his book, vastly expanded this and simplified their axioms to include a lot more theorems. All right, so in the realm of structures, we have that the universe K is going to be omega, right? Because we have a countable structure, so we can just assume that its universe is omega. That well ordering induces the copies of K inside of K as a subspace of the Baire space. And within that subspace, we're going to look for infinite dimensional Ramsey theory. So we'll say that K has infinite dimensional Ramsey theory if there's a subspace where it satisfies the Galvin-Perkery theorem, or even better, maybe the Ellentuck theorem. And the Big Ramsey degrees pose a constraint on this, because if you don't get down to one color for a finite set, how are you going to get down to one color for an infinite set, right? So you really have to develop the Big Ramsey degree theory before you can even start this question. So also in this KPT paper, they specifically asked to develop finite and infinite dimensional Ramsey theory for the rationals, the radograph, Henson graphs, generic posetsets, countable atomless Boolean algebra, and maybe one more. Big Ramsey degrees for these two had already been done by Dennis Devlin and Norbert Sauer and Laflamme and Vuksanovich. This one I proved upper bounds for, and then we got some exact bounds later. Generic poset, upper bounds were done by Jan Hubitschka, and then later exactly characterized by a large group of people. Countable atomless Boolean algebras are the first or second. The first example of this collection where we find out that there have infinite Big Ramsey degrees for sub-Boolean algebras with 3 or more atoms. Okay, so 2 quintessential examples that I'll go over are the Rado universals, Millikan theorem, and envelopes versus a different type of approach, which is Henson graphs and direct Ramsey theorems from Froissart structures using forcing. Okay, so Millikan's theorem, which many of you have seen this slide before over the years. Millikan's theorem is a Ramsey theorem for trees, where you're looking at a finitely branching tree with no terminal nodes. And given n greater or equal to 1, you have a notion of an n-strong subtree, which is just a subtree with n many levels that's fully branching inside the ambient tree. And Millikan showed that if you fix the n and you color all of the n-strong subtrees inside of this ambient tree, you can find a subtree which is infinite and again strong, where you have no more than one color for these copies. And there's also a product version for finitely many trees. There's also product versions for infinitely many trees, but you have to be more careful with those. Yeah, so a strong subtree is going to look like that. So a strong subtree is going to have levels where things branch. Everything at that level branches maximally inside the ambient tree, and then nothing else branches. So between the branching levels, you can choose different paths. So it's not like silver trees, which have to go the same ways. You can choose different paths between the levels that branch, but then at the branching levels, they have to branch maximally. So this is a red copy of a 3-strong subtree in here, and this is a blue copy of a 3-strong subtree in here, and Millikan's theorem would tell us that there is another strong subtree which is infinite, so no terminal nodes, where all of the copies of these 3 strong subtrees have one color. Okay. All right, and the Halpern-Leukli theorem is forming the pigeonhole in the proof of Millikan's theorem. So you do Halpern-Leukli, and then you do a bunch of induction on levels to get this Millikan theorem. All right, so the methodology with Millikan's theorem, which has been very successful for structures that don't have forbidden substructures, is as follows. This is the general outline of the procedure of how you would go through a proof for these things, is that you would fix a finite graph G, and then you would color the copies of G inside of your graph, your Rado graph in this instance. And then you realize that you can represent a universal graph in a very nice way as 2 to the less than omega. There's a way of encoding that as a universal graph. And then you apply the Millikan's theorem and envelopes of copies of G. So you have a copy of G inside of this universal graph. You can expand it to a strong tree or envelop it in a strong tree. And you can then shift your coloring from the structure to the strong tree, and then apply Millikan's theorem. And then after, so that gives you the upper bounds for the Big Ramsey degrees. And then after that, you can construct a diagonal anti-chain that represents a subcopy of the Rado graph. And then you have to do another argument to prove that that's optimal, okay? But this methodology works for the rationals in retrospect. It wasn't how it was originally proved, but you can see a proof of that in Todorcevic's book. It also works for the collection of unrestricted structures with finitely many binary relations, so like Rado graph, graphs with finitely many different edge relations, things like that. It also works for the rationals with n many different equivalence classes where each of them is dense, and the one for 2 ended up giving a particularly nice example in this paper. And then you can also use the product Millikan theorem for higher arity hypergraphs. So a picture of the proof of this idea of style of proof is you have your universal graph, which is being encoded in your tree, and you have some copy of a subgraph. In this case, it would be an edge, and you envelop it into a strong tree, transfer the coloring to this strong tree, apply the Millikan theorem, get one color for this type of edge. Okay, and then after that, you choose a diagonal anti-chain, as in Laflamme-Sauer-Vuksanovich, coding the Rado graph inside of the universal graph, and then showing that your bounds were optimal. All right, so the limitations of this method are that they don't work for Fryse structures that have forbidden substructures. It works great if you have a nice universal structure, but it won't work generally on homogeneous structures, except the exception is the rationals, or the rationals with n-many equivalence relations. And we would also really rather work directly on the homogeneous structures, in particular because this is necessary if you want to develop an infinite dimensional Ramsey theory. Okay, so two approaches. There's more approaches now, but at the time, there were just these two. So if you're a set theorist, and you're not sure if something's true at all in ZFC, you might try forcing it, right? That's what we do. So that's what I did. The Halpern-Loikli theorem, which is the pigeonhole for the Millikan theorem, has a lovely forcing style proof by Harrington, where he's using essentially Kappa-Cohen forcing and a name for a non-principal ultrafilter. But what he does is more in the style of recursion theory, where he uses the forcing to do an unbounded search for a finite object. The object is finite, therefore it's in the ground model, and you take it, and then you build your subtree. So this is an interesting style of proof, and it was a key for unlocking how to get big Ramsey degrees on more types of structures. Okay, so coding trees came about by knowing the Laflamme-Sauer-Vuksanovich proof and the end of their proof, and saying, okay, what if we start with what we know we want to get and work backwards, okay? So we'll actually work with the homogeneous structure that we intend to get in the end. And then after a couple of years, it became kind of clear that this is what was going on, that it was really just an enumeration of the structure and then looking at the induced substructure, looking at the induced tree of one types. So you can do this with any enumerated countable structure and find its tree of one types, and then you stick in these particular vertex nodes that code the structure that you care about inside of the tree of one types. So the radograph coding tree, of course, is everywhere branching. The coding tree for the triangle graph is, of course, not. Okay, so if you take any node in this tree and you look downwards and you take the set of those formulas, that is essentially the one type that that node is representing. All right, so forcing analogs of the Halpern-Loikli theorem for coding trees goes in this process, where you've fixed a finite subtree, and then you're fixing a level set, and you're coding all the copies of those level sets that have the structure that you care about so that you can get the coloring theorem for the big Ramsey degrees. So you take, just like with Harrington's proof, you would take a kappa that's large enough so you have the Erdős-Rado theorem to hold. You would make an appropriate notion of forcing, which is similar to Cohen forcing, but not exactly Cohen forcing, because it's taking into account the structure, and it's taking into account those things that are obstacles to extending a finite substructure to an infinite structure, and it's taking into account the difference between the nodes that are coding the actual structure and the nodes that are not. Okay, but you set that up as you need to, and then also, like Harrington's argument, you make a name for an ultrafilter on appropriate levels, and then you find a large set of conditions, kappa many different conditions, so that they're homogeneous in the same color for u dot many levels, and that's what you use to build your subtree taking care to make sure that you actually make a copy of your original structure as you go. So, but again, with this, you level by level, you set up your forcing, you find your nice homogeneous set of conditions, and then you use them to figure out where you should start building your subtree, and then you use them to find the next finite level where you should go to have one color. And everything you're building is in the ground model. You've never gone to a generic extension. Okay. All right, so that method.
From the point of view, the forcing is co-forcing, or?
It's not, exactly, because it has a more restricted partial order, and it also takes into account differences between the types of nodes. No, it should be just like regular kappa co-enforcing in that sense. I mean.
So forcing isomorphic co-enforcing.
Not forcing isomorphic, but would have the same properties in terms of collapsing or not.
Okay.
Yeah.
Will it be CCC?
No.
Okay.
No. All right, so that led to these results, and a couple of differences between the previous methodology was that these proofs directly reproduce your indivisibility, and also, so what I was really aiming for in this work was to get the infinite dimensional. And I got very close, but I didn't get it exactly, so we got it later. But it set up a lot of the pieces for the infinite dimensional, and it got some very good bounds. And independently, we got to exact bounds, and then this was subsumed in a later work with all 7 of us for all of the free amalgamation, finite relations, etc. And then more recently, it did bear fruition in terms of infinite dimensional Ramsey theory. All right, so here's where you could zone out if you wish to, because I have 10 very fast slides, just giving you an up-to-date of what's going on in this area. So the history started with Sierpinski, as Tanmay pointed out yesterday, and then it waited 4 decades, and then we had Erdős and Heinel and Posha show that the Big Ramsey degree for edges in the radograph is at least 2. And then we had Devlin's thesis work computing all Big Ramsey degrees for the rationals, and then we had some other vertex colorings and some more edge colorings, and then this other result that I have already mentioned. And then ultrametric spaces, which was another of the KPT problems, were actually fully computed. Some things on kappa that went on, and some more sorts of results using either Millikan's theorem or a new colored version of Millikan's theorem. All right, and then we had my results, and then things started moving again. So now I'm going to go rather quickly through these. Just, you've seen many of these older ones before. Now we're up to 2024, and we've got some new things going on. In particular, I will point out, because we'll talk about these in a little bit later, pseudotrees. And this is another instance where you have infinite Big Ramsey degrees. And these methods were what were used to help solve the Boolean algebra problem. But chains have finite Big Ramsey degrees. So this is the first instance where you have some finite structures having finite Big Ramsey degrees and also some finite structures having infinite Big Ramsey degrees. It's very interesting. We also have another result with infinite Big Ramsey degrees with infinitely many edges. Here's the countable Boolean algebra result that I mentioned before, and here's the 8 names written out. Okay, so that was last May they posted that. Still open for Boolean algebras with 2 atoms. And then more recently, we have counting Big Ramsey degrees of the 4-click-free Henson graph. And then some other things I'm going to talk about at the very end of this talk. All right, so pseudo-trees is one thing that's new. So we have some finite and some infinite Big Ramsey degrees. And this was a talk that Ola gave in Banff in 2018, which piqued my interest at the time, but I had no idea how to solve it, so it had to wait some years. But so dendrites are these continua that contain a closed simple curve. We have a notion of order, we have a notion of a ramification point, and we have these Wojcicki dendrites, which have these properties, that each arc contains a ramification point, but these are continua, so they're uncountable. It was proved that these are unique up to homeomorphism, and I'm not stating all of the previous work that's been done here, but some highlights are Kwiatkowska's work showing that if you have a finite collection of numbers which are between 3 and omega, then the universal minimal flow of the homeomorphism group of this dendrite is metrizable, and she computed it explicitly. And on the other hand, if P is an infinite set, then this homeomorphism group is not metrizable. Okay. And a point in the proof was showing that there is a precompact Ramsey expansion for the rooted version of the age of the set of all ramification points. So while the dendrite is a continuum, the set of ramification points is countable, and these are the points where the dendrite is branching, and it looks a lot like copies of the rationals where they have the branching points. And so the age of this is going to be a collection of trees, and if you root them, then you can find, or Ola found, that they have an expansion, which is Ramsey. Okay, so now if you have a Ramsey expansion of a class of finite structures, you might ask if its limit has Big Ramsey degrees. So I'll let Sai denote the 2-branching pseudo-tree, and this is induced by M with the just number 3. So you can think of it as a 2-branching tree, and a pseudo-tree is a tree-like structure, except that if you look downwards, if you take the collection of all predecessors of some node, then it's going to be a linear order, but not necessarily a well order. And you can define it concretely in this way. So we have an order, we have a notion of down. We're going to have an unrooted tree, but you can think of empty set as being a root in a case you just aren't coloring it. And everywhere you look, it's 2 branching at every node, and it's like infinitely many copies of the rationals. Okay, so I mentioned this result before, but I'll say it more slowly now. So in this paper, Hodansky, Eskew, and Weinert showed that the 2-branching pseudo-tree, they showed more in this paper, but in particular, they showed that the 2-branching pseudo-tree is indivisible, and that finite antichains have infinite Big Ramsey degree. And for that, they're using an oscillation method of Todorcevich. At the same time, they also found that chains of size 2 have a lower bound of 7. And then using some work, some other work, we found that the finite chains actually have finite Big Ramsey degrees. And in particular, for chains of size 2, We found an upper bound of @-7, so now we know the exact degrees for the chains. So this is the first Big Ramsey degree result for a Frise minus hereditary property class. And given the methods of the work, we seem to have exact bounds, but that remains to be just verified. The other nice thing about the approach to this proof using coding trees and forcing is that it's going to lend directly to getting a topological Ramsey space of subtrees, which are each of them pseudo-trees. But you have to be a little careful there. Okay, so the method here is going to be to set up a good enumeration of our pseudo-tree. So this is Sierpinski's idea of well-ordering your infinite structure. And then you're going to carefully set up your coding tree of quantifier-free complete one-types. And then we're going to prove Halpern-Loikley theorems using forcing. But there's a little twist on this one because you can't do it directly. You kind of have to come at it sideways to get things to work out. And then we use topological Ramsey space techniques. Okay, so this is a good enumeration of the pseudo-tree. And by good enumeration, you can mean several equivalent things. One way you could think of it as you've got the pseudo-tree over here, of which I have only drawn finitely much, okay? And, or at least, okay, you can think of these rays as copies of the rationals. And then we're going to pick out one by one some ordering of the nodes in this pseudo-tree. But we want to do it in such a way that at each stage we have an actual tree. Because we don't have the hereditary property, so you have to build a tree at each stage. Alternatively, you could think of it as enumerating the trees in some order so that each one is a substructure of the next. And so this enumeration here is going to induce a coding tree of one types by taking this node on your pseudo tree that you designated to be the 0th one and just sticking it at the bottom. And then you say, okay, what are my options here? I could either be below it, I could be down in this interval. I could be above it, which is in this interval. Or I could be starting a new ray, which is here. Okay. So you notice that the coding tree that gets induced by the pseudo tree has only the particular nodes that are coding nodes are branching and everything else is not. Okay, so it looks really similar to the coding tree for the rationals, except the differences are that we have 3 branching when it branches, and also that you have to distinguish between the middle branch and the other 2 because the middle branch is saying you're on a new ray. So you're keeping track of that. So one would like to prove a direct Ramsey theorem for these sorts of trees, but you'll find out that you run into some obstacles because if you look at extensions in your tree where more than one of them are changing rays at the same time, you'll get the oscillation map, which will get you something infinite, an infinite Big Ramsey degree. So you can't do that. So the way around it is to prove a Halpern-Loikley variant for one of these sorts of trees and then finitely many other perfect trees. So this is the Halpern-Loikley variant that we use, and it is proved by first making an amalgamation lemma of the style of the axiom A3 for the trees, then proving an end homogeneity theorem by a lot of induction and just using Halpern-Loikley with no forcing, and then using forcing to homogenize the end homogeneity, and then putting it all together by induction to get one color per type. So the analog to a diagonal antichain in this situation, you can't actually get an antichain because if you had an antichain, you are not going to code a subcopy of the pseudo tree. What you get is very close to it, an almost antichain where each of these nodes are not branching except they're extended by the middle branch, which is saying I'm starting a new ray here. So this is the optimal substructure, or Big Ramsey structure here. And then 7 types inside of here look like this in the sense of these trees. So in the pseudo tree, they're going to look like this. In the coding tree, they're going to look like this. I didn't draw them down here. And then the types or diaries that are giving you the exact degrees are going to look like this. Okay, so here you see the rationals, the Devlin types here. And then these other 5 are new. So you can imagine extrapolating these to the other types, and these look to be type bounds. All right, and now I present something which I'm a little nervous to present to this crowd. Please don't hate me, I have computability theory colleagues. All right, so my first postdoc was at Penn State with Steve Simpson, so I learned a little bit while I was there. And I learned enough to challenge people with good problems. And so I laid down the gauntlet with these different problem lists and a problem talk. And this led to this memoirs of Cholak, Doriak, Jafarov, Monin, and Pate, where they just whipped through the basics of, they basically, they set down the basics of computability theory for Halpern-Likely, Millikan theorem, rationals, and radograph. Okay, so some key results in there were that the Halpern-Likely theorem is provable from a recursive comprehension axiom. The Big Ramsey degree theorems are provable from the arithmetic comprehension axiom, which is stronger, and a couple of other things. So then a subset of these plus Liu got interested in the triangle-free graph, and Hubitschka's proof from the Carlson-Simpson theorem that the partial order has finite Big Ramsey degrees also gave an alternative and shorter proof of Big Ramsey degrees for H3, but with much looser bounds than the ones that I got. But using this theorem, they then showed that, in particular, the statement that the triangle-free Henson graph has finite Big Ramsey degrees is provable from ACA naught, which is equivalent to saying that you have omega plus 1 Turing jumps. Okay. But this is kind of like hitting a problem with a hammer, or something bigger than a hammer, very large hammer. Because so the only known proofs of Carlson-Simpson in terms of, so Carlson-Simpson implies Heinemann's theorem, and it's open at this point whether Heinemann's theorem is provable from less than ACA naught plus. So you can't get better using this approach, but you can get better using forcing. So we go back to our coding tree and we remind ourselves what this looks like. So now we're doing a very fine-tuned approach to exactly the structure we care about, not some encoding of it in some other wild structure. And we're going to use this very important theorem of Jockish that's been used in computability theory for many, 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 many things, which is a particular way of constructing computable colorings on subsets of n, so that any homogeneous subset is going to compute the n minus 2 Turing jump. And with Peter Cholak and Charlie McCoy, we extended that over to the coding trees, and And we're able to do two things. So these are lower bound arguments saying that you at least need this many Turing jumps to get finite Big Ramsey degrees for these particular structures. The first is about particular anti-cliques. So if you have your k greater or equal to 2 and your n greater or equal to 3, then the statement that these particular types of anti-cliques of size k have the Ramsey property and your n clique-free Henson graph codes the Turing jump, the 2k minus 2 Turing jump. And in particular, it shows that the statement finite Big Ramsey degrees of the n clique-free Henson graph needs the omega Turing jumps, right? So the lower bound just from this statement is that you need omega many Turing jumps. We also got a theorem for all graphs, which is nice, but I believe we could do much better on this one. For our anti-cliques, look like this. So recall the coding tree and recall that the left branch has no edges being coded on there. So an anti-clique of this form we're calling far because the first vertex in your graph, in your anti-clique, is at a level in the tree before the next one branches off. And then we can use these branching off levels as well as the terminal nodes to get our coloring. So it bumps us up to 2n minus 2 instead of just n minus 1. The closed graphs look like this. And we didn't get an exact result, but we got something that was, so we got the theorem I stated, but it doesn't go per diary, it goes per collection of diaries. More recently, with Henry Tausner, so this was not recent. He did this maybe 6 or 7 years ago, but he gave a new forcing style proof of Halper and Leukely, but without using the Erdős-Rado theorem, so no need for some uncountable cardinal kappa, and no need for, and this is part of his line of work, is trying to get rid of ultrafilters. And, which I like ultrafilters, but you know, okay, it's an interesting line of work, and it's been useful. So he sets up this mechanism for forcing with, you know, doing everything countably rather than a kappa, and adapting that style of forcing, and actually we reduced it down to kind of like an idea of combinatorial forcing where you have a statement or its negation, and you prove that once the statement holds, it's densely holding, and once its negation holds, it's densely holding. And so this is really a forcing style proof, but in the realm of computability theory, because we're not even using a partial order. But we adapted elements of this proof for the coding tree. And then the other thing you have to do differently is you have to dovetail all of the construction at once as you're building. You can't thin through, go into another level and thin through, because you're gonna add all these Turing jumps if you do that. But what we get then, this is theorem star, Asaf is gonna like this, because we need to finish checking everything, but it looks sound. And this is the statement that every finite triangle-free graph has finite Big Ramsey degrees, is then provable from omega many Turing jumps. So we got it to be an exact bound, and forcing was a key piece of this, because you have to do it very precisely on the structure you care about rather than coding it into some other structure that's a bit too wild to get what you want. Okay, and this result follows from what we really show, which is that given a diary for a finite triangle-free graph, so this is the structural expansion for which you will have the Ramsey property, then this thing has the Ramsey property in the Big Ramsey structure for H3 is provable from the nth Turing jump, where n is twice the number of levels in the diary. So forcing's useful at whatever level you're using it. It's set theory, ZFC, computability theory, and that is, almost the end. So these are my concluding thoughts. Big Ramsey degrees are characterized by enumerating the structure and categorizing the smallest and slowest essential changes that happen in the substructure. This is equivalent to looking for the Big Ramsey expansion. Exact Big Ramsey degrees and infinite dimensional Ramsey theory on homogeneous structures inherently really involve the tree of types because you've enumerated it and then it's just there. You can't get around it. A nice outcome has been the development of varying new methods, which I mentioned in my, 10 pages of what's happened since 2017. And forcing methods are really the way to achieve the fine-tuned results at whatever level you're looking. Okay. And that's it. Thank you.